Maybe now. How about now?
Yes.
Excellent.
Yes,
Yes.
yes. Yes.
Good.
Yeah, okay,
It's Victor.
Okay.
okay,
Sorry about the delay.
No
okay.
worries. Yeah, it's okay. Yeah.
Thank you very much, Ted, and thank you very much for having me here. I will try to I will try to do my best to finish my presentation on time. Okay, what you are looking at is yet another team which was somewhat born by the Desert Conference. So you can see some names. This is our team, and the sort of common denominator right now is a book which is going to be published shortly, which I am going to talk about. I have a pleasure of representing the whole group. I know that Professor Harchenko is with us. I know that Dr. Kochański is with us. I am not so sure about Professor Jastrzębinecki. I'm not so sure about Professor Van Gulik if they are with us. If they are, good morning. If they are not, it's my pleasure to do my best to represent our work. So next slide, please. This is what I'm going to talk about. I'm going to focus on certain results which came up from the idea of the Desert book. I'm trying to emphasize very strongly the importance of this Desert book as a source of inspiration, as a catalyst for a lot of things which resulted from the discussions during numerous Desert conferences I had the pleasure to attend. And also the presentation is twofold. I'm going to talk about the book and some parts of the book, and then the next part of the presentation will be done by Dr. Kochański. Next slide, please. Instead of sort of making an introduction whom I am, I would like to present this picture, which shows sort of snapshots from my life in different configurations. One of the most important picture in this picture is on this slide is the one in front of the nuclear reactor in Chernobyl, and it's my pleasure to have a joint photo with Professor Harchenko. Thank you very much for that, for this opportunity. You can also see Dr. Kochański on some of the pictures, including the one which is on the lower right corner. If you have a lot of imagination, you can recognize him as well. Next, please. Okay, so one of the things which we are trying to address is, as part of this conference, is to think about what is the upper border of the notion of dependability. So one of the things what we came up with as a result of this search is to develop a new discipline, which we are calling global trusted dependability. So I'm going to talk a little bit about that. I'm not going to dwell on each individual slides. I just send a signal that this notion of global trusted dependability is a part of the process which have been sort of thought over quite carefully and formalized from a mathematical standpoint. Next slide, please. Okay, what you are looking at is the outline of the book, and essentially each chapter of the book was prepared by different author. My part is number 5, chapter number 5, Global Trusted Dependability and Big Safety. And the introductory part is being worked out by Dr. Kochański. Next slide, please. So as I said, if you look at dependability per se, there are different definitions. On this slide, you can see sort of one of them as the ability of a system to deliver its intended level of service to its users. But the challenges represented by the situation on Earth clearly indicate that maybe we should form more ambitious and more global definitions of dependability. So one of the components which we believe is quite important to include is the notion of trust. So the combination of different factors, this globality, the question of trust, and how far we can go, ended up with a new definition of dependability, which is sort of provided here as the last sentence. It's somewhat called supremum dependability, even though I'm not so sure if this is the end of the story. But what is interesting in this definition, it does have an impact on something which is, I guess, one of the leading causes of our existence and the quality of our existence related to the notion of wellness. So through this global trusted dependability, we are trying to include new challenges and new problems, and not trying to be shy with them. We are trying to see what are the upper borders of our way of thinking and what we as scientists can do in that regard. That's the overall philosophy behind this global trusted dependability. Next slide, please. So the original story, and again, it was prompted by different factors, and the Desert Conference was one of them, was a question of where we stand as the human race in today's world. And I'm not going to say anything new here, that essentially the tone of this conference, based on my experience, is somewhat prompted by the question of artificial intelligence and the role of artificial intelligence. So our real world, governed by the humans, is being somewhat jeopardized and by another competitive factor, which is artificial intelligence. Next slide, please. So this artificial intelligence can be nicely represented by what's happening in the area of robotics. And since we are from New England, as you know, New England is a very strong center of robotics. So there is some animation prepared by Dr. Kochański. Ted, go ahead and show it to everybody, please. The father of those robots, Atlas and others, is Mark Rybert, who is right now in the process of building a 400 million facility in Cambridge, which is going to result most likely in the next generation of robots. We are looking forward to see what's cooking. So when you look at the slide, in reality, what happens, there are two worlds. There's one world, which is the real one, governed by us, and there's another one governed by artificial intelligence. But it's not sufficient, in our view, to represent the real environment, real universe we are in. There is also the third component, which we call the spiritual component for simplicity. But in reality, this model has been developed by ancient Greeks, because this is a typical Plato model, which is governed by physics, by mathematics, and by philosophy. So we are trying to sort of represent the modern universe using those ancient philosophical approaches, and they still resonate very well with our real world. So you can see the formal model on the right. Now, you can make this model deeper, you can look more detailed. This is an example of how this model can help to represent, I call it a supreme discipline of engineering called wellness engineering. And this is just a snapshot, the domain of this wellness engineering. You can see 9 fields here. Again, for the lack of time, I'm not going to dwell on it, but those 9 fields are related to identity, social life, knowledge, culture, economy, habitat, longevity, and innovation. Now, what is interesting with innovation, zero innovation means that you can have free time and you can do nothing, but you can also devote this free time and you can be busy with thinking, developing new things, and innovate things. So these are the consequences, just a simple sort of notion coming from the ancient Greek philosophers in the context of the 21st century. Next slide, please. So the model, since this is a graph, Markov chains can be applied here. The model which I'm talking about is also related to the theory of system-level diagnosis developed by Preparata, Chin, and Metz. And obviously, you can use different colors to indicate the status of individual nodes. Green meaning everything is okay, red meaning that it's faulty, and so on and so forth. So, and such an approach can be used to develop different scenarios. Very interesting. Next slide, please. Like, for example, we have been plagued by, we have this double sort disaster in the world. One is the coronavirus epidemics, and another one is the war situation and the danger of the Third World War. So, for example, if you look at the corona pandemic case, you can see that there are different scenarios possible. Again, you can see that in one case there may be a technology failure. This is this picture in the middle. The picture on the right may represent, let's say, the wrongdoing on part of humans. This red node with S. And there are consequences which you can see that our world is being spoiled by coronavirus. Next slide, please. A more detailed scenario, we still don't know exactly what has happened. There's a lot of uncertainty. This is an example of a dynamic scenario described by Ilya Aronov 2 years ago, which sort of resonates nicely with what we understand what happened. And as a result of this coronavirus epidemic, we essentially have the world which is still under attack of COVID. Next slide, please. Coming back to this Preparata model, one of the fundamental assumptions with this system-level diagnosis, I'm referring to the picture on the left, is the existence of fault-free core observer. So in this centralized picture, the observer is sort of independent and fault-free by definition. But as we know, it does not necessarily resonate with real-life scenarios. So it is possible to modify this model and integrate this centralized observer as part of the real domain. So we can see this in the picture on the right. And obviously you can do the same analysis, but with a different position of an observer. Next slide, please. You can also have models which are associated with this Preparata approach, when each node, the basic node in this reset model R, S, and T, is associated with an individual observer. The reason why I'm bringing this up, it was my research which was done several decades ago, which helped me to get my tenure at the University of New Hampshire. So it's quite important picture in my life. Next slide, please. That's another application of this approach, which allows you to use different matrices to evaluate the quality of life. What you are looking at is a modified picture of this wellness engineering, more formal. And you, in the most simplistic evaluation scheme, the most simplistic case, you can just apply binary values to each fields, and based on different prompts or information or knowledge, you can assign either zeros, which is bad, or ones, which is good, and you can summarize this and evaluate the quality of life. So I came up with the number 6 out of 9, and obviously going into the probability domain 0.67. This was my biased personal evaluated of the quality of life of myself a couple of months ago. Just as an example of an interesting thing. You can do it for a group of people, for a society, for the nation, and for the globe as well. Next slide, please. Now, another interesting observation which came from our research prompt, among other things, by the DESSERT community is the notion of fractal computing, developed by Dr. Koczański here. This is sort of a schematic thing of a modern network of computers, and this word fractal is the key factor here, the key fundamental factor here. What it is in reality is a network-based version of the basic von Neumann computer architecture model. Okay, so instead of having a single node, we have this plethora of living creatures, computing creatures surrounding us everywhere. And the nature of fractality is, as I said, quite important. It is so important that it also affects other areas of our life. Next slide, please. I was expecting a different slide here, but let me focus on this one. So, as I said, this notion of wellness engineering can be also put in a motion as a projection, which direction we are going. So you can see different stages associated, described as different subspecies of humans. So, for example, you have at the bottom Homo sapiens, everything is fine, and this avatar, this artificial intelligent thing, which is a next head next to this picture, is relatively small, showing who is the master, who dominates in this picture. Now, if you move to the next picture, you can see that the picture is, the situation is changing. And now you have sort of partners, so you have a twin situation. And humans are essentially addicted, depend on this avatar, artificial intelligence head or creature, represented, for example, by cellular phones. Now, because of the progress in artificial intelligence and our habits, which we do not control anymore, you can see another picture that AI is doing very well, but we are sort of following. So the idea is to try to understand the situation and change the picture, okay? That's why you have two other scenarios, which we do assume that there will be some kind of a partnership and balance between this real world and the artificial world. Next slide, please. I am showing the pictures from the book. Instead of this one is also interesting. I mentioned this very important aspect of fractality, and as a result, this is our attempt of representing what we do understand about what humans understand. This is the fractal tree of human knowledge. And there are different levels of abstractions coming from the lowest one representing engineering. Then the next stage is research, followed by science and science of science. And obviously on top is something which represents the word of understanding what we do not understand, or where we are heading, where we are going. Now, there are some principles here. For example, the principles of organization, we are trying to get better organized. That's the essence of progress. But there is also a notion, a basic notion of symmetry. So you can see that on the right-hand side, there are certain results of research, science, and engineering, which can be represented by symbols as golden apples. But at the same time, because of this symmetry principle, which is always there, we have negative aspects of knowledge, which are represented by those rotten apples. We showed them as in black for simplicity, because the picture is relatively small. So that's something, in our opinion, who we are right now in terms of our knowledge. And once again, this practicality is important. Next slide, please. This is my last slide. I would like to summarize and pay a tribute to the DESSERT conference and just emphasize different branches of what happened through our collaboration and friendship with our Ukrainian colleagues. You can see several threads here: freedom, scientific, organizational, and innovation. And you can read the text. And this is what happened, what has been happening over the last decades, several decades right now. I would like to end up with the innovation thread and emphasize that this innovation was probably one of the exciting and important aspects of this collaboration. So thank you very much, DESSERT, for that. And now, next. What's coming next? Well, there are different scenarios. One is described very nicely by Professor Harari from the Jerusalem University in Israel. And another one is going to be presented by Dr. Koczański. I would like to ask you not to ask questions, because I think this is a joint presentation, and it would be better to ask questions after Ted is going to finish his presentation. Thank you very much for your attention, and Ted, go ahead.
Well, thank you very much, Andrzej. From this point on, while Andrzej has been a source of inspiration and a little help on the side, he's not responsible particularly for the animation which follows. I kind of fell into an animation fixation for a couple of hours a few times. So the whole idea of this part of the thing is fusion energy being viewed as the new Promethean gift, or Teco Doro. For the people who are native Greek speakers, I apologize. The key remaining challenges to delivering practical fusion energy as a foundation for global safety and security, and I think it is the ultimate foundation for global safety and security, is proving that the decades of science experiments can scale to functioning reactor. And then we have as a model Enrico Fermi in the wartime conditions in the laboratory he built underneath the stadium for sports, created a working fission reactor in 1942. Now, this was under wartime conditions and wartime acceleration of things. It was a tour de force of technology and science. Note that the actual power output from this thing was a few watts. Now, this is, there unfortunately is nothing left of the original piece of technology, artistry. except for a couple random scraps like this little rack over here and things like that. And pictures even don't exist for the most part, except for artists' conceptions after the fact. So what had happened? Well, of course, the immediate achievement from this stage was the development of a functioning reactor to produce plutonium, which of course was used in the second atomic bomb, and of course in the first test of a nuclear explosion. But that took 3 years. It took another 15 years after that to bring a commercial reactor to the forefront. This is a composite here of timing and machines. This was the first actual reactor that was able to generate electricity commercially, but it used a naval reactor developed originally for the Nautilus submarine and modified slightly. So it's not really what we have out there now, though it may form the foundation for some of these all compact reactors, fission reactors that are being discussed and implemented. Dresden #1 was a breeder reactor experiment that was then converted into a commercial unit, but again, it didn't form the foundation for anything that went on from there. And Yankee Atomic, locally to here, about roughly 100 kilometers from where I'm sitting, is now been decommissioned, but it operated from essentially 1960 until the about 15 years ago or so. And it basically, you can see it's in a beautiful setting. It's a absolutely was a work of art in addition to work of technology. It didn't produce a lot of energy. That was producing about 180 megawatts electrical. But the benefits of fusion is that it first of all offers an ability to decouple fuel availability and the state of development of the place where it's being established. So in the case of the Yankee Atomic, you couldn't have done this in many places in the world at that time because there wasn't available technology, there wasn't available workers with the right kind of background, and it was just impossible. Similarly, right now, we depend on coal as our primary sources of energy and our primary sources of transportation energy in particular, but other, of course, electric grid as well. And right now, this limits the places where this can be deployed, again, for a number of reasons. It offers essentially dependable, inexhaustible energy. We talk about dependability. It's inexhaustible because essentially the oceans are full of hydrogen. Scaled on any scaling within reason to a global scale from a very localized system. And it allows you to turn on energy anytime and anywhere. You don't have to wait for the sun to rise or the wind to blow. This morning when I woke up getting ready for this thing, I was consuming a little over 2 kilowatts, making myself a piece of toast and a espresso. The two machines each consumed about 1 kilowatt. So I hope everybody likes Prometheus. Fusion energy in one easy lesson. It will take a couple of minutes, hopefully. Why fusion is worth doing, why fusion has been hard to do, specific solution, which I think is the path right now, magnetic fusion and tokamaks in particular, paying appropriate homage to the people who, starting in the 1950s, developed the tokamak in the Soviet Union, and then once it was released to the rest of the world, in part through the visit to the laboratory by a team of scientists who sort of provided a check on the claims of the Soviet scientists that came. These people came from the Cullum Laboratory in England, and they have since become a major player in the game. So the traditional path has been from the T3 machine. There's actually a T1 and a T2 and a few others, but the T3 was the well-known one that was released to the world in the second IAEA global conference, to JET, the Joint European Torus, and the path is now following on to ITER, which is a giant construction project in the south of France. But there's an alternative. And the alternative has been pioneered by people from MIT who ended up coming up with a plan to build on the high field, magnetic field use with a machine that would be much smaller than ITER, but very similar output capabilities. And there's a couple of intermediate steps there. So the big challenge, of course, is up to now, we have been able to make fast neutrons, and a fair number of them have come out of this machine over here. But so far, we don't have any way of making electricity. Now, the steps are fairly straightforward. You take the neutrons, you absorb them in a lithium blanket, and it gets hot. It also breeds tritium, which you need because the two elements of the fuel are both forms of hydrogen, one of which is not uncommon because the ocean's filled with it, but the other one, which is very hard to come by because it has a short half-life. So anything that was made by the Big Bang or whatever, or any of the other processes, has a half-life that half of it disappears in about 10 years. So most of the tritium now in the world is coming from Canada, where there are a number of heavy water reactors called CANDU reactors. Can't depend on them, though, for supplying the tritium. You have to breed it in the blanket. Once you do that, you have the hot blanket material, which can produce steam and drive a conventional turbo alternator, and voila, because it's a European project, and Eureka, because its ultimate heritage goes back to Archimedes and the ancient Greeks. Electricity for the grid. Emphasize that. Okay, so why is fusion worth doing it? Well, E equals mc squared provides a lot of energy for a small amount of fuel. You convert and tritium, two forms of hydrogen, you bang them together, and you make helium. And there's a small amount of mass that's lost in the process, some of which comes out as a neutron and some of which comes out as a fast-moving helium. You'll see there's megavolt of energies coming out as the neutron, and about a little less than 4 mega electron volts comes out in the moving helium. You have to save the helium because you need to keep things hot, and the neutron then bangs into a lithium in the blanket and produces more helium, and at 4.8 MeV, very similar to this, and then it produces a recoiling which comes out of it, and you separate the helium and the tritium. You put the tritium back into here, and basically the temperature of this blanket then ends up around 600 degrees centigrade. For comparison with coal and oil and natural gas are similar, for 1,000 megawatt traditional plant size, or a coal plant power plant size, and natural gas plant usually a little smaller, 1,000 megawatts, 2.7 million tons of coal is needed per year. If you do it with fusion, it's 250 kilos of fuel per year. This power of the EMC squared. Water provides you essentially an unlimited supply of hydrogen and lithium. A single gallon of seawater could produce as much energy as 300 gallons of gasoline. It provides concentrated power not achievable with wind or solar. There's minimal nuclear waste issues not achievable with fission. and there are minimal nuclear proliferation issues. But it's hard to do. Why? Because this picture right here. Energy, this is distance. Where you want to be is here, where the strong nuclear force will pull the pieces together, but they're both charged and they repel each other. So you have to overcome this hill here. And most of the particles will scatter off each other. And that's why confinement is important. Operating temperature to do this is about 100 million degrees thereabouts, Celsius or Kelvin, doesn't really matter because that's a little small offset. You start going from a solid to a liquid to a gas to a plasma. Well, most of the time we're starting as a gas and we make it into a plasma, though there is a need to control certain aspects of the discharge. And so people are actually injecting chunks of frozen deuterium into plasmas so this whole process occurs inside. The particles are charged because in a plasma you have a mixture of electrons and protons, and so you can control them with a magnetic field. And this is what the magnetic field looks like in a sort of notional sense, because you have to take account of the fact the magnetic field naturally would be stronger on the inside than on the outside, and so you need to compensate for that, and also stability things come up. So the tokamak is essentially a step-down transformer. You have in the earliest tokamaks an iron yoke with a primary over here, not shown, and you drive a current in the plasma. That's the secondary. You also have some additional coils that basically provide essentially stabilization of things. So this is BT that's produced by these green things over here. There's also this vertical field coil that handles this hoop stress. And this is the T3 tokamak at the Kurchatov Institute circa 1965. It was in operation since the early 60s. They kept on working on it a little bit. And you can see this copper shell was here, which used to provide the equilibrium and stability before the advent of feedback controls, some of which I had the pleasure of working on when I was at MIT as an undergraduate. So we step it forward a little bit, and the Europeans got together and started building a machine in the Culham Laboratory near Oxford. And in 1997, they produced until a few months ago, world record amount of fusion energy, but that was then beaten by the second round of it, 59 megajoules. So somebody says, well, we haven't made fusion yet. Well, we have made fusion. It's just not economical yet. That's what it looked like a few months ago. This glow over here is hydrogen that is mostly neutral hydrogen on the outside edge of the discharge, and some ionized hydrogen, and particles are moving back and forth because some of the neutral hydrogen diffuses inward, and there's a process called charge exchange where two hydrogens bang into each other and the charge flips, so you end up with a fast moving neutral, which you have to deal with. And then there's this area down here that is the process used for removing the waste and also controlling the discharge, and that's called the diverter. And this is glowing diverter because there's a lot of power going into it. Actual two discharges. This is from the first generation of deuterium tritium in jet. That was in 1997, and this is in 2022. You see the duration of the power is 5 seconds in both cases, and you need 575 megawatts, though, to run the copper magnets. And so mostly whenever they want to run the machine, they have to get permission from the British electric utility governing body, because they could bring the entire power system down in that area. and especially nowadays where they have shortages of electricity. This was a statement from the late Bernard Bigot, who was Director General of ITER. He passed away a few months after the statement. A sustained pulse of deuterium and tritium fusion at this power level, nearly industrial scale, delivers a resounding confirmation to all of those involved in the global fusion quest. Agree with that. Then he goes on, because of course he was Director General of ITER, and said that we're on the right track. Well, I think that's not the case, really. So this is interesting. This is how big this machine is. It's not big, but it's big enough a person can get inside. The history from 78, it started construction, first plasma, and it was in 1983. That's what you need surrounding this. This is inside of this area right here. The rest of this, as they describe it, is an aircraft hangar size hall. And that's that discharge again. This is a sort of an artist's conception of what the thing looks like, not counting all that really external stuff. These are the magnetic field coils. That's not an iron core. These are frames that hold these copper coils, because in fact, when you're dealing with this very large magnetic field, and this is about 7,000 times the Earth's magnetic field, when you're dealing with that big a magnetic field with this big of a volume, the forces are immense forces. The other thing you have to deal with, of course, is that when it runs, it becomes mildly radioactive because of the neutrons bombarding everything in sight as they're passing on through. And so you have to have a robot if you want to do work on the inside when it's hot. It's sort of by the European path to ITER. They started construction in the 90s. It's estimated to be finished in the 2025, 2027. This is two artist conceptions, but the scaling is correct. That's jet, and this is ITER. You can drive a truck around inside of this as opposed to walk around inside. And this is the construction site. Apologize for the quality of the image. In the south of France, and very nice area. This is the main hall where you can see some large building cranes that are building this very large structure, because, again, just like in the case of the big hall at JET, you have a big hall that's really a big hall. There's a huge crane that can handle 100-ton pieces that you move around inside as you need to, and stuff like that. So, as I said, besides the core, you need a bunch of other stuff to make electricity. You need a steam generator. You need to separate the isotopes from the blanket. You need to let the helium go because you don't care. It's harmless stuff. And then you have to basically have a remote handling system and a current drive system and a heating system and all these external things. So here's the other way. MIT started working on this little thing. Actually, it was an earlier one that's sort of like the Soviet T3 that was called Alcator A. I had my arms up to my elbows in industrial cleaning solvents when we had to fix a problem when we had a electrical inside the machine. They rebuilt it, and they have followed this design path. That's what the Alcator C mod machine looked like.
You exceeded your time by 5 minutes already.
Okay, well, I'll be out of here in 5 minutes.
Yes, less than 5 minutes.
Okay, so here's the record high pressure discharge that proved that you could do it the high magnetic field way. And this is what the inside of an old tokamak looks like. This thing operated for 20 plus years, and you can see it looks kind of beat up. So here's several hundred tokamaks and other miscellaneous things that have been involved in this challenge over the past 50 years to get to this place right here. This is the goal. Essentially, it's called ignition. This is where the fusion provides all the energy. You don't need any external energy. And these machines here won't get there. They're trying to achieve Q equals 10, which is sufficient to make a commercial reactor, because you actually need to get here to be break even, but you have all that external equipment that you have to power, and that gets you there. This is from the people at Commonwealth Fusion Systems. This is basically test magnet they just did a year ago. And this is the machine they're building now. This is the challenge to get to this one. This is the actual one that will produce electric power from the grid, that people working at the lab in Cambridge, but the new lab is about 40 kilometers west of here. And basically, there's lots of engineering that's involved. This is high temperature superconducting material, which enables them to go to the high magnetic fields. This is what the notional reactor looks like. These are big pieces of steel to take care of those enormous forces. And the key thing that they have come up with, that they probably have patents on, is building it using these high temperature superconducting coils that can be broken. So you don't have to have a single piece like you do at ITER, which makes it almost impossible to get the vacuum chamber out when you need to. This thing can be disassembled. Details. So Spark will be the test bed for ARC. This is all the surrounding stuff that will not be there. This will be part of ARC that's not there for Spark. And the goal is to do these experiments to get to the confirming that you really are on the path to ARC. So now I'll wrap up. This is the notional path. This is, they expect their Spark to start operating in 2025. They expect in a short period after that to get to Q equals 1 and then Q equals 2. That's akin to what Fermi did, essentially. And then by the end of this decade, essentially, they begin construction on the ARC machine and maybe have a functioning reactor sometime in the middle 30s. And that's what the site looks like now. There's another building where they're making the magnets, but this is the site for the actual Spark machine. These are big, thick concrete walls to contain the explosion of the magnetic system in case something happens. And they've did this. It says 2 months. It's actually now 3 months, but in any event. So here's Professor Roshinsky's business card. And I would like to say to the people who are familiar with the language of ancient Greece, Ευχαριστώ πάρα πολύ, καλά Χριστούγεννα και ευτυχισμό στο νέο έτος.
Your pronunciation is excellent, better than Greeks. Thank you very much.
Well, I studied Greek, unfortunately, and have little to show for it, but there you go. So I'm done now, and we're open to questions if we have any time.
Thank you very much, both of you professors. Very nice, very interesting, these keynote speakers. Please, any questions, please?
After such presentations, is it time for very deep thinking about this information? Okay.
Yes, very interesting. I have a question that in Greece, in countries like Greece, which the earthquake is in high risk, how is the safety, this kind of fashion that you mentioned?
Yeah, so
we have to be careless about that because nowadays it's very important. We have the question: what about this kind of energy? Can we use it at at the end or no? Because accidents is very often, and it's important for us to think about that.
Yeah, there are some issues that have to be resolved. For instance, there will be a few grams of tritium in the reactor core at any instant of time. Now, tritium is radioactive, but it's also hydrogen, and so it's lighter than air. So if you open the building up, it vents the atmosphere, and probably a few grams of tritium dissipates very quickly in the air. If you contaminate somebody with tritium, the standard treatment is to send the person home for the weekend with a case of beer. Because of course it's hydrogen, so it combines with everything and makes water in your body, and then it gets flushed out. As far as the other parts of it that are radioactive, the structure can become mildly radioactive, but it's a short-term radioactivity, and it can't spread anywhere. And that's why you would confine the mechanical parts in case they blew apart to stay inside that big concrete box.
Yeah, thank you very much. Yes, Professor Robert Strait, please.
Hi, Ted. This is Bob Strait, Andre's colleague. Great presentation. Hey, I had a quick question. I was Googling real quick to see, is anybody looking at trying to contain the fusion with the electric fields rather than magnetic to see?
Oh, yeah.
Is that going on? How's that going?
Well, all those kind of things are down here. Low temperatures and very low product of density and confinement time, which means on this scale, which is logarithmic, as you can see, they're factors of thousands away from the goal. That's where things like this was the Model C stellarator. It actually came out about the same time as the T3 tokamak. This was in Princeton, and it led to the ST tokamak, which was the first Princeton tokamak over here. The stellarator, some people think, is better because it doesn't require plasma current. It creates a magnetic field by a complex external magnetic field, but because of the product of these construction issues, the state-of-the-art stellarator is here somewhere. It's Wendelstein. It's in Deutsch, and I don't see it here, but it's here somewhere. It would be a stellarator, so it would be in here somewhere probably. It's still a factor of about between 100 and 10 times away from the goal. These other ones are even stranger machines of various kinds that have a lot of science to do before they can be considered to be real challengers to the tokamak.
Okay, thank you.
Not that there aren't people raising money to try to do them.
Thank you very much for the question for us, sir.
Okay.
And
Sorry,
please, Professor.
can I ask you, I don't know, this question can be addressed to Professor Rusinski and Professor Kochansky. My question is the following. You talked about big safety. And in context of nuclear power plants as well and new reactors generation as well. Now one of the trends in nuclear is development and implementation small module reactor. What about, can small module reactor make big safety small safety or not? Your opinion concerning such distributed SMR reactors in point of view safety and digital infrastructure, because in this case we have not only reactor part, we have generation part, transmission part, and of course, different kind of IT will be embedded, will be implemented. Maybe my question is not question, it's more discussion. Okay, concerning.
Well, certainly the U.S. Department of Energy is very committed to developing a practical small modular reactor, and there are a number of commercial firms that are working with the Department of Energy, and they will have one functioning sometime in the next year or two. They're also in Korea and in Japan. They're looking at them. So I understand there's also a group in Europe that is working on trying to produce a functioning small modular nuclear reactor. And the biggest advantage of that, of course, is a closed package that essentially follows the trajectory used by the naval reactors. The latest generation of naval reactors, like the newest submarines and the aircraft carrier Gerald Ford, have a 50-year core that you just basically close it up, and then when it's finished its lifetime, you take it away. And that gets rid of a lot of the issues that are associated with decommissioning and stuff like that. I think the biggest challenge with the small modular reactors, though, is siting. I think you're going to have people who will be opposed to the idea that you're putting a fission reactor in near a city. It's like you have right now, near where Andrzej lives, there is a reactor that is called Seabrook on the New Hampshire coast, and there was a plan to build a second unit, but it was blocked by people who threw pig's blood onto the thing and made all kinds of nasty demonstrations with no violence, but a lot of objection, and it was canceled as a result.
Thank you.
I would point out one other thing that I didn't say anything about the computing that's needed for this. I was thinking about it, but I left it out. However, after seeing the great presentation about the satellite data, the experiments that are doing produce hundreds of gigabytes in a given day, maybe more than a terabyte in a given day. The experiments at the engineering level will probably produce a little less data, but there will be an enormous amount of AI involved, because controls to keep the machines from the so-called disruptive instability, which can damage the vessel, are being developed right as we talk. And there's an experiment going on in Switzerland, actually, it's relatively small tokamak, that's AI controlled.
Thank you. And Professor Robert Strait, a comment? Yes?
Yes. I posted a link on the chat for everybody, but I've been involved with a modular nuclear program for the last 3 or 4 years that the Department of Defense is working on. It's called the PELE project, PELE. I put a link up there so people can see it, but we're using a triso particles is the name of the fuel we're using, trying to address some of the things that Ted was talking about. That's, I guess the prototypes are coming out this next year to be tested, and then, we're doing it. But Ted did bring up a good point. One of the issues is, even though you have this thing, you can load it on the back of a truck. It comes in a shipping container. You can put it on an airplane and fly it anywhere in the world. You can't, from a legal standpoint, you can't do that because everybody's afraid of the nuclear issues. So, it may be interesting for folks to look at. Obviously, it's a DoD thing, so there's a lot of classified pieces to it. But they do have public information that they're sharing if anybody's interested.
Yes, thank you very much. Thank you very much. Any more questions?
if it's possible, I would like to ask Professor Rusinski concerning his unique tree, science of science. Andrzej, please, your comments concerning this idea, this paradigm, in context of any recommendation, any conclusions for IT engineers or engineers in the area safety and security domain, because it is your vision of future science, and what about safety and security issues in this context? Thank you. Sorry, switch on, please. Your
I forgot. As you know, forgetting things is becoming my next specialty. So it's sorry about that. Now, can you hear me? Can you hear me?
Yes, yes, we can hear.
yes.
Okay. Thank you very much for this question. There is several fundamental aspects of the answer I would like to give, and because of time, I will be very short, and I apologize for that. The first fundamental answer is that we have to, as I said, try to build a taxonomy, the paradigm, so we know and we understand what we do know. Okay, and because of this principle of asymmetry, we also have to pose a question of, is it possible and should we know and understand what we do not know? Because those issues become, pretty obvious. I don't want to sound trivial, but as we know, any new discovery is causing more questions than answers. And this process is sort of expands. So this should lead to understanding the state of the multiverse, where we are and where we are heading. Now, obviously, there will be a question of organization and complexity. So another question is, can we, even though our minds does not have any indications that we have reached the borders, how far we can think, but from the engineering, from the practicality, from the management, from the logistics standpoint, is it possible for us to organize a system, build a system similar to tokamak or whatever, so we can monitor and manage our knowledge? So that's an open question. Well, my theory is that we cannot do that because there will be not enough resources and not enough ways of essentially monitoring ourselves and going beyond the solar system and other things. So from that standpoint, the question of employing artificial intelligence, big data, and so when we are talking about big data, it's not big data, it's something, in terms of the continuum and further infinity type of questions, that we have to consider AI as a helper, as something which is going to help us to understand what we do know and what we do not know. So it goes without saying. So from that standpoint, it's not just a question of philosophical things, who is going to know better than humans, and it's not just a question who is going to make decisions, but it's a question for us from the standpoint of big safety and security. So from this is what my answer is, that because of this reality and where we are heading and who we are and what's going to happen, we have challenges from the standpoint of safety and security unprecedented in the history of our civilization. At this point, our new book is the answer that one of the answers is global trusted dependability, but it's only a very small section of what we, in reality, what we are facing. So, but on the other hand, I do believe that who we are and as scientists, what we are working on, we can address this issue and we can definitely have a better understanding and specific solutions for those very, very big grand challenges. Okay, so that's my answer.
Thank you very much for your answer. I think we need use these three to think every day about our sense of our life, sense of our civilization, and so on. Thank you. Thank you very much.
And our mission as scientists, you know, we are facing new tasks as scientists. Our mission is not to understand and to observe and to discover, but also to be responsible and be sort of responsible for safety and security. That's our new mission as scientists.
Yes, thank you. And one more question, Professor Shmilova.
I have a little question. Thank you for report. Very interesting about energy. You know, this is a big problem for Kyiv, for Ukraine, and for me too. But a little question about development of location of station, of location of reactor. Maybe in future, location of reactor in airspace. Maybe, and delivery of energy using satellites. What do you think about this? Satellites, many satellites, but energy in airspace as one driver. Information in airspace, EV connection to information, but your energy. Maybe in future, location in airspace too? What do you think about location?
Well, I think there's been many studies over many years. There was a fairly thorough exploration both by Arthur D. Little, the former company, a Cambridge consulting company, and by Raytheon, using microwaves to beam energy from a solar array in space down to the Earth. And it was up to the point where they were talking about launching a little prototype to try it. But the problem was in terms of pointing the beam, the energy in the beam has to be fairly high in order to make it economical. You can't spread out the receiving antenna over too large an area. So then the energy in the beam is potentially a problem because it can eat birds and cook them, or cook the birds, then you can eat them after they fall out of the sky. This sort of went on the back burner. Now, would you do the same thing with fusion? Well, there are a lot of people talking about using fusion for space propulsion, and certainly to put the reactor on the moon, for instance, or the reactor on Mars, or reactor on a high velocity spacecraft going to Alpha Centauri or something. Actually putting it in an orbit for powering ground, I think it has the same issues as the solar array, that beam energy is very high density, and you have risks. And certainly there would be a lot of public concern because they've seen a lot of movies where people get ideas of things like that and use them to
No, this is the idea. Thank you. I understood. No, this is the idea. Maybe in future, with the distance, big distance, but maybe this is safe for us, safe for people, and delivering for always for connect, distance connect. Maybe.
Well,
this is a new technology. Maybe new technology and the advantages of new technology for this. No, thank you. Very interesting.
Yeah, I mean, I think you can imagine it, but I think it's certainly not in the near term. I think in the near term, the goal of this thing is to put reactors in either in the place where there were existing fission plants that have been decommissioned, but they're still holding bunches of leftover spent fuel rods. So the land is still restricted, and all you need is a small piece of it for the fusion plant, or even replacing the coal burning part of a coal burning power plant with a fusion reactor.
Thank you. interesting.
Thank you very much for your questions and for answers. It was very useful for us to understand or to think about that, because the problem that we think is a lot, and of course we're not sleeping very well about that, and I think that we'll have to work a lot on that. Thank you very much to all of you. And now we're finishing the session of keynote speakers for today. And yes, we'll have a small shift of our time. Let's give 15 minutes for coffee break, and we will start two sessions in 16:15. So I'm writing also in the chat. Thank you.
Okay, dear colleagues, I would like add concerning our next sessions. It will be two separate special sessions, which continue topics of big data, big satellite data analysis, and the second session will be related to dependability for space systems, more radio electronic system. Hence, we invite all our participants, not only presenters, for participation in these two sessions. Now, as said Professor Bardis, we have a short break. Concerning tomorrow, our work, we will start as today at 9 a.m. Tomorrow we will have a mixed mode. Part of participants will participate in plenary session and session of line in officer club in the center of Athens. All presentation will be translated by online. Hence, we have work according with our program. Thank you one more for your participation in this session. And now, if you have any question, please, your question.
Yes, please.
Please.
It's a low. One ask to speak.
Any questions? Please repeat if you have.
Okay.
No, I see a chairman of one of the special session, Professor Simeon Zhila.
Yes, good evening.
Yes, we will start at 10 minutes later. Okay. Hence, now it's time for break. Thank you once more for very interesting discussion and very interesting presentation. Thank you.